to the trial and error, and those should be off. And in those notes, in some cases, and we haven't gone there, we haven't gone to the detailed situation where I say, here's the phase margin I want, and here's the frequency I want it at. That's what you're referring to. It's a little more advanced than what I give in my steps. In my steps, we don't care what the frequency is, and so it's a lot easier that way. That's why you need a cushion, though. It brings up an interesting point, because if you have a lead lag, let's just really quickly sketch out the lead compensator steps, okay? So you have a plant that has a frequency response plot that looks like this. This is M of omega in dB, and this is theta of omega. Or phi of omega, I don't care, whatever you want to call it. All right? Okay? So now, let's go to the first case where we don't specify a theta or an omega crossover. All right? In the first case, you say, all right, I want you to now design it. You've already established your steady state error, right? So this has to be a unity static gain compensator. So that when you let S go to 0, it's 1, and you don't mess up your error, right? So we're on that page? Okay. So then what you do is you say, all right, let's go to let's get the current phase margin of the closed loop, right? Step 1, get the current phase margin of the closed loop. So how do you do that? You go to the gain crossover frequency, which is 0 dB. This is open loop, by the way. Remember, we're getting closed loop information from the open loop. Don't forget that. That's huge. Simple concept, but boy, if you start using the closed loop system, FRF, to get the phase margin of the closed loop, the whole thing goes to Hades in a hell basket. Okay? So, all right, then what do? We get the phase margin. So suppose the phase margin is minus 10 degrees. So this is minus 180, right? Correct? All right, now let's suppose we want a phase margin of plus 30. Okay? So what do? You say, well, my current phase margin is minus 10. I need plus 30. My compensator has to give me 40 degrees of phase. Except I know that I'm going to be moving to the right with the crossover frequency, because remember that compensator, what it's going to do is at the maximum phase, that compensator adds alpha dB over 2. So this whole thing gets shifted up and the gain shifts over to the right where the phase is even less than negative 10. So you say, okay, I want 40 plus 5 or 10. That's the cushion that I talked about, right? Remember that? Am I going too fast here? The key thing that some people don't catch right away is the fact that this compensator looks like this. On log frequency axis, there's your phase. This is what you're designing for. This is my phi max, right? I got phi max of 40 degrees because I had minus 10 and I wanted 30. Right? But also when I apply that thing, the magnitude of this thing goes from here up to here, up to here. So the amplitude is increased by alpha dB over 2. And remember, when you multiply things, these blocks together, dBs add. That's the beauty about decibels, right? Rather than multiplying things, you just add things. It's a lot easier than multiplying. So what happens when you put this thing in, if you put it here, if you design it so you choose that as your gain crossover, what's going to happen is this magnitude is going to have gone up by alpha dB over 2. So even though you got your phase here is up from minus 10 or negative 190 up to 160, it's not the gain crossover anymore. So it's moved, right? So what you have to do is you have to acknowledge that this is going to happen, and then you have to say, well, I think it's going to happen somewhere over here. So I'm going to, and this phase is going to be going down further. Now, if the phase goes back up, well, heck then, you know, you're in better shape. But usually phase keeps dropping over frequency. So what you do is you say, okay, I want 40 degrees plus 5. That's 5 degree cushion, right? So then what you do is you compute alpha. Don't you? You've got these two equations, right? You have the phase margin, right? That's one equation. And you have alpha. That gives you your two equations and two unknowns, omega 1, omega 2. You'll find out then what you do is you find the omega gain, you find the omega max, right, from the compensator, because remember that there's omega 1 and omega 2, but omega max is the square root of omega 1, omega 2. So once you find the omega 1, omega 2 from those two equations, you get omega max. Correct? Following? Then you say, well, where do I want to put this omega? Where do I want to put my compensator? Well, I want to put it where the magnitude is currently down alpha dB over 2. Because I know it's going to raise it up alpha dB, and that's going to be my crossover. All right? So you go to where you're down alpha dB over 2, say here, where this is down alpha dB over 2. And then you go to the phase here, and if that phase isn't a whole lot different than minus 10 or 190, suppose it's 195, boom, you're done. If it's 200, 210, because it's really dropping fast, time to iterate.
So like 5 or 10 degrees should be okay?
5 to 10 degrees, usually. Now, he brought up a more advanced problem, which is the following. What if I told you that I wanted that gain crossover to stay where it is? Now I'm telling you, you have to put the compensator here. And in a way it's easier, but the problem is, you put it here, you're going to get your 30 degrees here, aren't you? Because that's exactly where you're putting it. You've got 40 degrees on the compensator, it's minus 10 here. You're going to get negative 150 degrees here. Everything's fine except this thing is up alpha dB over 2. Now design a second compensator, unity static gain, that will knock that thing down to 0 dB without changing the phase. That's the lag. So remember, this is the lag compensator. The lead compensator goes up, the lag compensator goes down. So the lag compensator has a phase that looks like this, right? It's subtracting phase. But it also has a magnitude that looks like this. It's unity static gain. So what it does is it goes like this. Correct? Right? It just flips from the lead compensator because it's a lag. Now, I want to use an animal like this so that it won't screw up the phase at that frequency. That phase is at negative 150 degrees, and I don't want to touch it. It's perfect. I just want to knock the magnitude down by that alpha. Suppose that alpha dB over 2 was 10 dB. This is an example. That means I want to use this compensator as a high frequency attenuator with no change in the phase. No change in the phase. Where does this thing not change in the phase? Well, way out here is where it doesn't change. The phase is back to 0. Right? And what's this value? Well, I want this to be minus 10 dB. So this is the region I'm using my lag compensator in. So what I do is I say, okay, I know this phase is back to 0 at 10 omega 2 or 10 omega 1. I'm going to go to 50 omega 1. And then it's really back to 0. So 50 omega 1 is right here, right? And I want alpha to be minus 10 dB. Okay. So how do I design this compensator? Well, I've got my two equations right here. You choose, remember, there's the frequency. What is 50 omega 1? 50 omega 1 is this guy. Because that's where I want the phase of my lag compensator to be back to 0. So that gives me one equation. 50, remember, the lag compensator has an omega 1, omega 2 as well, right? So 50, and in fact they flip omega 2 and omega 1. But this is the one equation. It says that this guy is 50 times my lower frequency of my lag compensator. That's one equation. So you find that first frequency of the compensator. You also find from its alpha the omega 2 over omega 1. And now you have your two equations and your two unknowns. And what that compensator will do to this thing is it'll screw around with the phase down here, way down here, right, which you don't care about. But by the time it gets back up to here, it's going to take that thing and bring it back down 10 dB. So that's what you were looking at. You were looking at the lead-lag combination for more specifications than need for the exam. Any other questions on the exam? Yes? No?
So I got a question on how to do 2C S1 and
We already talked about how you cancel a pole.
But how to achieve the error state of for the ramp input?
It's a type 1 system. You've had homeworks on that, and it's discussed in the book. When you've got a type 1 closed loop system, it is type 1, isn't it? Does everybody see the type number? Because we didn't get rid of that 1 over S. We got rid of the 1 over S plus 1. Because the controller has an S plus 1 in the numerator. So that goes away, but the 1 over S is still there. So the closed loop will still be type 1. It'll still have finite non-zero steady state error for a ramp. So you simply compute that steady state error for a ramp. In this problem, it's not for a unit ramp. It's for the biggest slope ramp with gamma. But that's just a constant. The authors talk about these K sub V and K sub A, these steady state error constants. You're looking at K sub V because it's a velocity or type 1 system. But please, again, don't forget gamma in that thing. Those error constants are just that. They're constants. And to say that the steady state error is 1 over kV is incorrect. In the book, it is correct for an input which is a unit ramp. The error is 1 over kV. You don't have a unit ramp. It's gamma over kV. All right? Other questions?
Problem 3C, what exactly is that input file showing? I know we're supposed to use...
ICBM?
Yeah, what exactly
Did you type size?
I'm sorry.
This is 3C, it's the
Yes.
ICBM
Yes.
file?
What exactly is
You
that?
loaded it.
Yes.
Did you file it?
No.
Do size, ICBM. And what is that going to give you?
Depends what you used to read it in it.
What? You just load ICBM.text.
Like the load command.
The load. That's it. How did you read it into your workspace?
I've tried a few different ways, but you can get just a massive one-column array.
I don't know what command you're using to put that into your workspace.
Well, I've got it figured now, it's just,
Okay, you do.
yeah.
We've done this in previous homeworks. We've used that. You guys know a lot more about MATLAB than I do. There may be 50 different ways of loading files in. I'm a simple person. Load the file. Using load. Other people have emailed me and I really don't even have any idea what commands you're using, so I really can't help you.
And then how are we supposed to?
And then type size. And when you type size, ICBM, it'll tell you it's 2 by, it's a very long array. I forget how long it is. But 32,000 plus. Right? It's a long array. And the first column is, what do you think? Time. So if you wanted to plot that, just to make sure you got it entered into your workspace, right, then you'd say plot ICBM all rows, or no, this is actually, it's not this, or was it this? Is it 2 by? Okay, so it is 2 by, so you'd say 1, comma, colon. That's the x coordinate or the time coordinate, comma, ICBM 2, comma, colon. And you should get that plot that's given there, just to verify that you're working with the right data. And it also, I mean, you really should, rather than doing this, why don't you just immediately say T is equal to ICBM first column, all rows. Why? Because you're going to need this in your LSIM. And rather than typing ICBM, blah, 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 this is dangerous because it's got 1, 2, 3, 4, 5, 6, 7, 8, 9 symbols in it. In any kind of mistype, if you don't know how to type and I don't know how to type, it's going to be really frustrating. So if I get the typing right once and I call it T, then in LSIM I put U equals what? ICBM.
So the second column is position.
It's angular position relative to horizon for that antenna. Yep. Then you'd say U equals, or whatever you want to call it, ICBM 2. Other questions? Yes.
So for number 2, just like a units question.
Where are we at here?
So like just in general, like
Okay.
you change it to RPM for volt.
In general,
And then,
I think we're up at part A right now. aren't we?
Well, and then your input is like your command is time, like seconds, right?
Yeah.
And then so then is your output then just rotations?
What are you talking about?
Well, like, cause it's RPM for volt.
That's the DC motor as a velocity system. That's what you buy off the shelf. It says this many RPM per volt. But you're going to use it as a positioning system. So you want it degrees per second instead of RPM per volt. Degrees per second. RPM is revolutions per second per volt. You want to change revolutions revolutions per minute per volt. You want to change it to degrees per second per volt.
So I think what he might be asking is, does that first part have any role in the rest of the question? Are we supposed to use the results from part A in?
No, you're already given it. In fact, you're supposed to find the RPM. If again, this is a modification of a prior exam where I actually started by giving the students the RPM per volt, and then said, now you're going to use this as a positioning system. Find out what the transfer function will be in degrees per second, in the degrees per volt.
So we just use degrees per volt for the rest of the problem.
This, yeah, I mean, this problem, part A, has nothing to do with the rest of the problem. It just has to do with Where did you get your motor from? It's a lot easy. This is a safe. I would like to think I'm Mother Teresa, but I have too many other habits. If I gave you something in RPM per volt and you got this wrong, the whole rest of the problem sucks. Right? Because you're using it as a positioning system. So rather than being overly kind to you, I was really trying to be overly kind to myself so I don't have to grade problems B, C, D, and E based on an incorrect part A. So I gave you this, but tell me what it came from. And after that, you don't need it. Other questions? Does that answer it? Yes.
Okay, this is gonna be really dumb, but I'm still having trouble with this.
Take your hat off and let your brain air out a little more, and maybe you'll feel more intelligent. No, you can put your hat back on.
Still having
Except it contrasts you. Take your hat off. I mean, you got a good do there, but you're sitting next to Elvis. I mean, it just doesn't work.
I don't even try.
Go ahead.
I'm still having trouble with 1B arriving at the three-dimensional approximate transfer function.
Yeah.
I have something.
Did you get it in a fortune cookie?
No, like I worked it out.
He's got this little strip of paper. I just had a fortune cookie yesterday, so that's the first thing that came to my mind. Imagine, wouldn't that be trippy if you bit into a fortune cookie and it gave you the exam to answer the problem 1C? So what's up?
Okay, so I arrived at an approximate, a three-dimensional approximate.
Because you did a pole zero cancellation.
Right.
So what was a 4D? I call it 4D because in state space it is 4D. And it's just an acronym that makes life easier. This is a fourth order system. With three zeros, right? But when you have a zero canceling a pole, this gets knocked down to second order, this gets to third order. That's it, but now be careful because you have to make sure the static gain is still the same. That's the only key. Is that your question with static gain?
That might be part of it. Is it possible if I just read you what I have and then you can say that's right or that's not right? Or you can just tell me. Well, I know. Okay.
You're more than welcome. In fact, I want you to read what's on that little card.
Okay.
Just for giggles.
Well, okay.
So everybody now, listen.
So my numerator is s squared minus 0.1482s plus 0.154.
Whatever, it's the second degree
Yeah.
polynomial.
And then the bottom is third.
Yeah. Okay, got that. Sounds
Right.
good.
Okay. So then my static gain comes out to something that's not 0.5, which is
Well then, I guess you need to change it.
right, and I did.
Just
and
by
then-
multiplying by 1 over that static gain. Take the whole your whole reduced transfer function. If the static gain is 3, right? You let s equal to 0 on your reduced order transfer function. If it's 3 and you want it to be a half, what do you multiply by? 1/6. The whole thing times 1/6 will be 3/6. Does everybody see that? It's a little thing, but if you don't get the static gains to match up, then you're comparing apples to oranges in the reduced order system. Make sense now?
Yeah.
Other questions? Yes.
For the first design problem, if I found a controller that works the steady state,
Where are we?
it is 2C.
Whatever the first design problem is.
Oh, the design problem, yes.
So if I found a controller that makes the steady state error go to 0, should I look for a simpler controller for the steady state error?
Your controller must have a pole of the origin. The only way you can get the steady state error to a ramp to be 0 is if the closed loop is type 2. And you now have a type 1, right? It's a type 1 now, so your controller must be adding another pole at the origin to make it type 2 so that you have 0 steady state error for a ramp. And that won't work. Okay. All right, let's look at the poles here. Look at this thing. Remember, it's 120. What's the open loop right now? The open loop right now, because this doesn't exist, never has, it's always been a pigment of your exaggeration. This is the open loop. Okay? Got it? Now you want a controller that cancels that. So the controller has to have an S plus 1 in the numerator. Right? So we know that the form of the controller I was going to be sloppier, if that's even possible. So the controller as is looks like this. Given you half the problem, that was the whole point of that first part was to do you know what pole zero cancellation is, and I've been, so you all know now, if you get that one wrong, you deserve it. All right, so what you've done is you've put this in the denominator, haven't you? The only way, if you do it correctly, that you can get 0 steady state error for a ramp is if the closed loop system is type 2, which means finite non-zero error for a parabola. So let's assume that you put a controller like this in here. So there's your controller. What's your plan? What's your open loop? Correct? Got it? What's the root locus for the closed loop? Start with plotting your x's and zeros. Where are your x's? Please, thank you. Where are your zeros? What's the root locus? Oh, nothing? There's 2 poles and there's 2 zeros at infinity. Is there anything on the real axis? Are you to the left of an odd number of x's and or zeros? No, this is an even number. Prove that this point is not on the root locus. Well, what does that one give you? 180. What does the second one give you? 180. That's 360. It's not an odd multiple of 180. Prove that every point along the imaginary axis is on the root locus. What does this one give you? The second one give you? 180. So here's your root locus. Now tell me about the closed loop steady state error. Tell me. There is none. Remember, to compute steady state error, you actually have to have a stable system. Just because you get a finite number for a steady state error does not mean you will have a steady state error if the system is unstable. You'll still get a number, but the number is irrelevant. So be careful with it. You have to have something that looks like this, where this is non-zero. Or everything is beyond that point won't work.
What's the command for steady state error? How do you find that?
Command?
Or is there,
You mean a MATLAB command?
is there one?
I mean, you tell me, is there one? Did anybody find one? No, what I just do is, remember the command input is theta C, right? And your output is theta. So once you compute using LSIM with input theta c, you compute theta, and then you just take theta c minus theta and you plot it, and you'll find it out. And the other reason for plotting it instead of just using a command that would give you one is, even if it told you that the steady state error, there was a command that says, yeah, you've achieved your steady state error, by plotting it, you see how long did it take me to get that steady state error. Right? Other questions? Yes?
So for the last homework, like we did, in the steady state error, we did the input of like 1 is going to be like 1 over t squared.
1 over s squared.
Or, yeah, 1 over s squared. So that if we...
Because why? Why did you use 1 over s squared?
Well, because I think we went from prime to
Right, but what does 1 over s squared correspond to? T.
T.
Yes, it corresponds to a unit ramp. T. But if your ramp is gamma t, what do you get for its Laplace?
Okay, so
Gamma over s squared.
Okay.
Other questions?
I'm a bit confused on problem 1. I think maybe
It's asking if you understand what a frequency response function is.
How do we relate the wiggle of the rudder stick to the yaw rate?
That's a good question. In fact, that is the question. How fast are you wiggling?
The frequency of 1.6 hertz.
Do you think that frequency has any bearing on the problem? You've got an input, which is a sinusoid, at 1.6 hertz. What's the output going to be? What's the structure of the output going to be in the steady state? Come on. Wax on. Wax off. Sign in. Sign out. What happens to the sign? Frequency stays the same. Only 2 things change. Its amplitude changes by the magnitude of the FRF at that frequency, and its phase changes by the phase of the FRF at that frequency. This plot that we had up here before, I've done this plot so many times. Here's an accelerometer's FRF. Why do you not want to be measuring accelerations at that frequency? Because a given acceleration at this frequency isn't going to scale like a constant. It's going to be amplified by the actual sensor. So you may have a very low amplitude here for true acceleration, but when you measure it with an accelerometer, because you're at the accelerometer's resonance, it's going to be magnified by this many dB. Remember, with sensors, ideally, with a sensor, you want a flat FRF. That way, all acceleration is all voltage. So many volts per G. Which frequency? No, all frequencies. Just volts per G. Volts per G. That's what you want for a sensor, right? But not every sensor has a flat FRF. And if you operate at up here, it's going to amplify that many dB and tell you you've got an acceleration which is maybe 50 times greater than what it really is. Because you're not measuring acceleration, you're measuring the resonance of the accelerometer. Okay, so that kind of a semi-obtuse. Other questions? Yes.
So for parts B, are we using the transfer function that we did or are we take one?
What else would you use?
Oh, you should use the revamp one.
this, all of it use the reduced order transfer function. If you do it right, you should find that the reduced order FRF and impulse response are dead on.
Okay.
So at that point, keep it simple and use the simpler one.
Okay.
Yes?
For a target event, would you also be able to do that using Wilson and just see what the amplitude comes out as?
No. I want you to actually compute it. I want to know if you know what an FRF is. If it was so complicated, I would have said, this is difficult, so use a simulation to see what you get. But thank you for getting me to clarify that. I want you to use the FRF directly to compute what you're going to see in the yaw rate. Okay? Other questions? Alrighty then, let's get into the hard stuff, which is chapter 7. Now, I was looking over this over the weekend, and by the way, how many people in here have signed up for 432? Anybody? I noticed that there are 9 people currently signed up for. Anybody sign up for 573? Okay, just curiosity question. The reason I ask is because Bong Wee has taught 432 in the past and has had my students coming into 432. And he expects them, because Bong Wee and Ping Lu both, but Bong in particular, he's a hardcore state-based guy. So when you walk in 432, you better know about controllability and transformation and all the mathematics of this stuff. And so he says, Peter, you're not teaching these people anything. And I said, no, Bong, I'm teaching them concepts. You want to teach them modern controls in the second semester? Yes, teach them state space hardcore, fine. But don't expect that somebody coming in from my 331 sections is going to be a state space guru. They're going to know what transfer functions are. They're going to know what frequency response functions are. They're going to know what the dynamic parameters zeta, omega n, omega d are. They're going to have a really solid basis in the basics, but they're not going to be math files. They're not going to know this stuff. And that's why I tell you, I taught it at Purdue. I taught it for Purdue for 7 years till they kicked me out. True. Did I tell you why they kicked me out? No. It was a hoot! It was a hoot! Yeah, you got to the engineering college and these guys said, what's going on here with you people in ME? Sherman would have gotten tenure in our department. And you could have heard a pin drop, because E at Purdue is the worst. You know E's in almost any college. So when they said that I would have gotten tenure in their department, there was a small quiet. And then the professor in ME says, well, you see, when Sherman came here 7 years ago, he got the worst instructor ratings of anyone in the department. And now he's getting the best ratings of anyone in the department. And we think the only reason he became so good is he's desperate to get tenure. And we think if we give him tenure, he's going to revert to bad teaching. And you know what their response was? Equally quiet. Because it is apparent they didn't want me there. I don't know why. Such a lovable guy. So anyway, I taught at Purdue for 7 years, and I taught modern controls, and I taught the controls, senior level controls, and the systems. Even after 3 courses, we had measurement systems, then we had block diagrams and manipulating block diagrams. That was course 2. And then a senior level course in controls. We did not teach state space in any of those 3 courses. I taught state space in the graduate level course, so that the students coming into the graduate level course could now learn the mathematics of multidimensional systems, but they know the concepts. So because you guys have only basically 1 course, I think it's obscene that you should be focusing on this kind of stuff. But your arrows, MEs, arrow. Double E. But we're going to go through it because I need to prepare you for this. You are arrows, and arrows do a lot of state space. I gave a whole lecture on motivating this stuff. So let's go through this stuff very quickly now to see what are you going to be required of to know in Chapter 7. Okay, they give a description of a state space system with X1 and X2. That's example 7.1. I'm not going to go through that, but you've seen this. You actually saw this in 355, right? This is 355. Now, you didn't emphasize this much in 355, because why did you emphasize this and not this? Because all the stability information about the plane is right here. All you do is Ike, right? You do Ike and you can tell me about the stability, you can tell me about time constants, you know, doubling time, damping, you can tell me everything about this stability, about the stability dynamics from here. But we also have an output. So this is a little thing, and I talked about it in my section, but not to any real degree. You're all familiar with this. And I'm assuming that when I go through this right now, because I'm going to skim through some of it and say, you should know this. They give you examples, satellite control of a model in a state variable form. You should all be able to reformulate satellite control in a state variable form. Okay. There it is. All right? Are you all comfortable with satellite position control in state variable form? Well, let's just look at the transfer function of a satellite. Simple satellite. What is it? You have a satellite, right? It's got this antenna on it, or this solar panel on it. It's trying to suck its, get energy from the sun. So it's moving its angular position. When you give it an impulse, what happens to that angular position? Come on, I have a satellite, it's rotating. It's stationary right here. If I give it a pulse, a torque pulse, what does it do? It rotates. For how long?
Doesn't stop it.
Forever. There's nothing to dampen out that spinning. If it were on the planet Earth with air, it would die out. So you have a transfer function which looks like this. Right? Okay. What's the differential equation? That's not the differential equation, but it's easy to get the dq from here, isn't it? What is it? Powers of S there should be a C here. There's the dq. Right? So what you do for your state variable, you say x1 is theta dot, x2 is theta. All right? Got that? Now what does this differential equation become? And what's x2 dot? And how do I put that in state form? I told you, when I write state equations, always leave big blanks. And then just take your equations and start filling in the rows. So what's the first one? X1 dot, right, is what? And what about X2 dot? That's one form. If you look at this picture right here, my one is down here, their one is up there. Who's right? Which one's right? Well, it's likely the book's right, because I didn't write the book. Who's right? How many vote for the book? Chickens. How many vote for me? You'll do very well in politics and marriage. They're both right. They're both right. They just chose state variable x2 to be theta dot and x1 to be theta. You can choose them any way you want. Okay, so there are multiple representations of state systems, and we've got 2 minutes left here. Some people apparently had to get the pizza before they sell out. And so if you get a different state model than what the authors get, it's simply because you define your state variables differently. All right? So that's a little thing, example 7.2, cruise control. You can look at the cruise control example. They end up getting an A, B, C, D matrix set. Then they go to the everybody's favorite example, the bridge T circuit. You know what a bridge T circuit is? It's an electrical circuit. You guys could beat that leads.
But it's bridged.
It's not very exciting, I must say, so I'm going to ignore it. What we'll do next time is we'll get into block diagrams and stuff form. Okay? So, if you're finished with the exam, read this stuff over. I should have the homework related to chapter 7 posted by this evening.